When we talk about T, we're talking about timing. Say, okay, you have this position, but at this time, which time? And when we're giving a time, we need to give the time scale. The main goal of a GNSS positioning system is to compute what we call a PVT. PVT is a positioning, velocity, and timing. Okay, or we call as well a PNT, positioning, navigation, and time. One of the first things when we are talking about PVT is position. What does it mean, position? When we are talking about position, we talk about X, Y, Z. Or this is in a Cartesian reference frame, and we have different reference frames. But in any case, when we talk about position, we talk about reference frame. When we talk about T, we're talking about timing. Say, okay, you have this position, but at this time, which time? And when we're giving a time, we need to give the time scale, okay? Because it's, I tell you, now it's 10 a.m. Now you in local time Toronto. I'm in Toronto. Local time Toronto is 10 a.m. now, but it's 16 or let's say 4 p.m. in Europe. It depends on the reference time scale that you give. You have different times. When we are using GPS, the reference time scale is what we call the GPST, GPS time scale. And we're talking about Galileo, we call about the GST, the Galileo System Time. But if you're talking, for example, in local time Toronto and local time Madrid, they are different time scales, yes? Because we have a difference of 6 hours. And these 6 hours we call the offset, time scale offset between two reference time scales, okay? Then between Toronto and Madrid, we have 6 hours of time scale offset. Between GPS and Galileo, we have an offset, which is the Galileo GPS time offset between both of them. Then, even though they both are atomic time scales, which are very precise atomic scales, they are very close to each other, but they are not perfectly synchronized one to each other. Then we have a few nanoseconds of synchronization between GPS and Galileo system time. We are really close to each other, but they are not exactly the same. A few nanoseconds or centimeter levels in the case of the reference frame. GPS time, the GPS time 0, the origin of the GPS time is put in 6 January 1980 at 000000. The GST, Galileo system time, started on the 22 September 1999 at 000. 22 of September of 1999. And you can say, how is it possible the Galileo system time started in 1999? We didn't have even a Galileo system yet. Galileo system was operational big years later. EGNOS has an internal ENT time. We will call EGNOS network time. The origin of this is 22 of September 1999 at 000, which is exactly the same origin as the Galileo time. What is the offset between these two origins? It's exactly 1024 weeks. Why we decided to put the origin exactly at 1024 weeks? GPS time, we usually decompose in GPS week or GPS week number, and also what we call the TOW, time of week, which is the seconds of a week, then number of weeks and seconds in the week, yes? But when in the navigation, GPS is providing in the navigation message the information about the week, it only provides the week in 10 bits. 10 bits. It means that with 10 bits, we can only go to 1024 weeks. Not more than this. What does it mean? That every 1024 weeks, this will go to 0 again. It reset to 0. And then second rollover, and then third rollover. Yes, if you remember, 2 years ago, I think it was the 9 April 2019, we have the second rollover of GPS, second row. It was 20,048 weeks later. In Galileo, we will use 12 bits. With 12 bits, we can go to 4,098 98 weeks. Then we have a rollover every 80 years. In GPS, it's every 20 years. In Galileo, we encode the GPS, the Galileo week, in 12 bits. Then we can go, we'll have a rollover 78, 80 years. That's why we decided to put the same origin in order to make sure that the first rollover of GPS, we start the Galileo. Galileo and GPS, they are, the time is based on atomic clocks. It means it's very stable in time, both, right? It means that between both the origin, we have an offset always of this. The computation of this time scale using measurements, because at the end you have to estimate this time, right? It makes that even if both are atomic clocks, they are not really synchronized perfectly. They have some nanoseconds desynchronization. The offset between both time scales is what we call the GGTO, Galileo GPS time offset. One of the most important concepts in GNSS is the desynchronization. For example, if I tell you what time is it to all of you, you will tell me a different time, because your time, your watches or your clocks will be desynchronized with regards to your local time by few seconds, maybe few minutes or whatever. Yes. Then some of you will be advanced, or some of you will be delayed with regards to the perfect time. Yes. This is what we call the clock offset or the clock bias between your time and the time scale reference. If I tell you, for example, what time is it? And you tell me it's 4 and 2 minutes. And in reality, it's 4, you will be desynchronized of 2 minutes. But if I tell you, what time is it? 4:02, but I want you to give me the synchronization error or offset with regards to another time scale, instead of your local time in Madrid or in Europe, right? I want you to tell me which is your desynchronization with regards to the local time in Toronto. What will be the value? 6 hours plus 2 minutes. Your desynchronization will be, in local time of Toronto, will be 6 hours and 2 minutes. In local time of Europe will be 2 minutes. Then, depending on the time scale you are, your desynchronization will be different, even though the value is the same. But you have to take into account this offset between time scales. It means that if I have a time scale GPS here, and I have a Galileo time scale here, and I give you my clock, the bias, with respect to Galileo, the clock, the bias of the satellite, for example, will be this value. Let's imagine this is something like 1 millisecond of the synchronization. This clock will have a synchronization of 1 millisecond plus this GGTO with another time scale. Then the offset, the clock is the same, yes? But the synchronization depends on the time scale you are referring to, this desynchronization. If I have several clocks, let's imagine I have several satellites, okay? And I have several desynchronization of this satellite with regards to a Galileo system time. And I have the clock as well with regards to the GPS time scale. Then let's imagine I have this BE with regards to Galileo, and then BE GPS. I know these values. I know them. The desynchronization with regards to Galileo and the desynchronization with regards to GPS. Let's imagine that I want to estimate the offset between both time scales. Someone can tell me how to estimate the offset between time scales if I have the values of the clocks in two different time scales? Do you agree with me that if I make an average of BE Galileo minus BE GPS divided by the number of satellites, this will be an estimation of the offset? I take all of the satellites, I take the difference between GPS and Galileo, which is an estimation of the offset, different estimations of the offset, and the average will be the offset, an estimation of this offset. That's why when we are estimating time scale offsets, it depends on how many satellites you use, how many measurements you use. That's why this offset is never the same. Because depending who is estimating and how it's estimating, the offset will be an estimation of this, but never the perfect value.